Oh, it's on. Okay. All right. Good afternoon, everyone. So this is our paper session 40-something about displays and projectors. Emerging display and projectors technologies. Thank you for coming. And I'm the session chair Yuta from the University of Tokyo, Japan. So we have 4 papers about exciting new AR displays and projection technologies. And time is limited, so let's start. So the first speaker is Hiroki Kusuyama. So can you please start, if you're ready?
Thank you for introduction and attending my presentation. Hello everyone, I'm Hiroki Kusuyama from Osaka University. Today we will introduce a novel projector that can achieve both shadow suppression and deblurring by using multiple lenses with different aperture. Projection mapping technology has a fundamental and critical problem. Cast shadows like this. And in interactive projection mapping system, as shown in the left, it's the common situation that the user's bodies block the projection light as they approach the target. The resultant shadow makes the projected image partially invisible, and the user's sense of immersion will be reduced. The most common approach to shadow suppression is synthetic aperture, which is called the multi-projection system. In this approach, the multiple projectors are distributed so that we can project the images onto the target surface from different spatial positions. And when one projector is occluded, a compensating image is generated so that other projectors can cover that area. However, in most cases, we need to achieve geometrical and color consistency among these projectors, and this results in delay in shadow suppression. Another approach is the large aperture projection using a large format optical elements. In this approach, we can achieve shadow suppression with a single projector because the projection lights are focused from so wide viewing angle. In previous research, a micro-mirror array plate, which is one of the retrotransmissive optics, is used as a large format optics. But this is not a lens, so we cannot implement functions typical of optical lens-based systems such as zoom-in. Therefore, we utilize a large aperture Fresnel lens as the large format optics in this research. This figure is our large aperture projector. The large aperture projector can suppress cast shadows, but the projected results are known to be significantly blurred due to its shallow depth of field. As a result, the high frequency components in the target image are lost. Then, we drill a hole in the center of the Fresnel lens and add the extra projector that is equipped with the standard aperture lens. This project compensates for the residuals, in other words, the high frequency components that is attenuated in the large aperture projection. We call this the residual projector. Then let's think of a simultaneous projection with these two projectors. We can suppress cast shadows, and at the same time, we can achieve deblurring of the large aperture projector. These two different projectors are aligned on the same optical axis to eliminate the need for geometrical registration. To summarize, in non-shadow areas, we can see a clear image due to its residual projection, and in shadow areas, the residual projection is entirely blocked due to its small aperture. However, the colors and textures are roughly remain. We believe that this is more preferable than the hard shadow as like in the standard projection in terms of user experience. This is the actual prototype of our proposed system. The objects shown in red are the components of the large aperture projector, and the blue objects are the residual projector. And we utilized a large aperture Fresnel lens, which diameter is 500 millimeters, and the focal length is the 250 millimeters. And we drilled a center of the hole in the center of the Fresnel lens at a diameter of 30 millimeters. Next, we introduce how to generate the projection images. First, we capture the point split function, PSF, of the large aperture projector to simulate the blur of the large aperture projection. Point split function is the impulse function of the projection system, and we can acquire these kind of PSFs by projecting the dot pattern to the surface and capturing these projected dot pattern by using an RGB camera. Here, most of the previous research used the Gaussian distribution for the PSF estimation, in other words, the PSF fitting. However, the luminance distribution of the PSF in our large aperture projector is more extensive than the standard conventional projector. So we need the more heavy-tailed distribution. In this research, we focused on a T distribution, which is the general form of the Gaussian distribution. The right two figures show the fitting results of these two kinds of models. Gray line is the actual captured PSF, and the red line is the Gaussian distribution, and blue line is our distribution using the T distribution. And as a result, our model represents the actual PSF more closely than the conventional Gaussian model. So far, we could acquire the PSF of the large aperture projector, but how can we optimize the projection images? Our projection system consists of two kinds of projectors, large aperture and residual projector. So we need to optimize two kinds of projection images. Our optimization framework is divided in two steps. First, we set the target image as the large aperture projection image and calculate the simulated blurred image by using estimated PSF. And by calculating the MSE loss between target image and simulated blurred image, we can update the large aperture projection image. By using this sharpened input image, we can simulate the blurred image again, and we can calculate the residuals by subtracting this image from the target image. These residuals are clumped from 0 to 255 to input this image to the residual projector. And after that, the blurred image and residuals are added together to simulate the final result with two projectors. And by calculating the MSE loss between target image and simulated final result, we can update two kinds of projection images. We repeated these processes for 10 times, and we acquired the optimal projection images. This video shows the actual projected results in different projection conditions. In standard projection, we can see a clear image on the bunny target. However, a part of the image is lost due to the cast shadows. On the other hand, in large aperture projection, we can suppress cast shadows. However, the projected results are significantly blurred due to its shallow depth of field. And in proposed method, we can see a clear image in non-shadow areas. In shadow areas, the projected results are slightly blurred. However, it's not the hard shadow as like in the standard projection. To validate our deblurring method, we performed the image quality assessment by using a white planar surface as the projection target. The projection conditions are the same as the video, and by using the target image shown in the left, the projected results are captured by using a RGB camera. In with occluder condition, we placed a human hand-like occluder at a distance of 250 millimeters from the target surface. And as a result, in all metrics for the image quality assessment, PSNR, SSIM, and DISTS, the evaluation value of proposed method is higher than the large aperture only projection condition. And in with occluder condition, the proposed method acquired the highest score in these three kinds of conditions. In addition, we conducted a user study on hand interactive projection mapping to investigate how the proposed method affects the task execution of the user. The same projection conditions are used also in this study. And our hypothesis is a user completes tasks faster and has fewer mistakes in proposed method compared to other conditions. In this study, we used a pen tablet as a projection target to implement the interactive projection mapping application, as shown in the video. In this task, participants traced the large characters by using a pen and following the order of the small characters written above. This one. And in addition, considering scenarios, there is another moving user. We placed additional occluder, wooden hand occluder, and we moved this occluder at the speed of 10 millimeter per second. And this inhibits the task execution of the user. We measured the task completion time and the number of mistakes in this study. And this is the result of the user study. Regarding the completion time, in the proposed method, the participants complete the tasks significantly faster than other conditions. And about the number of mistakes in proposed method, the participants had fewer mistakes than the large aperture only projection. These results suggest that the proposed method has a potential to enhance the task's performance in the interactive projection mapping application. Here is a summary of this presentation. As our future direction, we have some technical limitations. One is the shallow depth of field, and another is the long calculation time for the optimization of the projection image. We consider that coding the lens aperture and the deep learning-based projection image generation is one of the solutions for these kind of technical limitations. Thank you for your attention.
Okay, great talk, Hiroki. So any questions about this new projection system from the audiences? Okay, Bruce.
Bruce Thomas, University of South Australia. What's for the standard high frequency projector, what's the angle of that? It looks like that was a pretty narrow field of view that projector was projecting at.
Yeah, the projected size of the residual projector is the same as the large aperture projector. So the projected size is relatively narrow compared to the standard projector.
So what is the angle that you can, the field of view angle?
Okay.
Oh, sorry, I can look in the paper, that's okay.
The projected size of the similar to the display panel because of the lens formula. But in this setup, we placed lens the half of the distance of target and the display panel, and by using lens formula, the projected size will be the same as the display panel.
Oh, okay.
Similar.
Okay, thank you very much.
Thank you.
Other questions? Actually, I also have a question for, in particular, this slide. So you put the hole at the center of the Fresnel lens. I feel like it's better to, can we also have a hole somewhere else in the peripheral of the Fresnel lens? Because I feel like the center region of the Fresnel lens is the most rich area that you can utilize the light source of the original projector.
You mean you don't need, we don't need to drill a hole?
I mean, no. Can we, is it somehow, why you put the hole at the center? Is it some design factor, or what's the reason you have at the center of the other big lens?
Yeah, thank you. We need to, we wanted to align these projectors on the same optical axis. So we drilled a hole in the center of the Fresnel lens.
Why you have to align the optical centers?
To eliminate the need for geometrical registration.
Okay, thank you. Yeah, we still have maybe one more question. Okay, Shohei.
Hello, nice talk. I'm Shohei Morin from University of Stuttgart. In the optimization framework, I think you are only updating the input images, but can you just further update BSF during this, within optimization pipeline?
I'm sorry, could you repeat the last sentence?
Can you further update the PSF as well,
Mm-hmm.
as well as the input images within this framework?
PSF,
Mm-hmm.
but we capture the PSF directory, and the PSF is a constant in this optimization.
So yeah, I understand that, but what I wanted to mention was like, that PSF still have some, could be the case that it still have some errors in it, right, through your calibration. So then it's optimized once, but probably, jointly optimizing these inputs and also the PSF further a bit would improve your image quality. That's my point.
I'm sorry, I couldn't catch up the optimization also in the PSF.
Yeah, so you can probably back propagate the loss into the PSF as well. Maybe.
I'm sorry, I had.
Yeah, let's talk that later.
I have not tried that kind of optimization. Thank you.
Okay, maybe it's a possible next cooperation now happening. So, okay, thank you again for Hiroki for the great talk. So let's move on to the next talk then.
Thank you for your attention.
Yeah. By the way, his talk and the next talk are also both journal papers, and the next talk is from Christoph Ebner. About near see-through about optical see-through display.
Okay, again, I'm Christoph Ebner. Thanks for coming. I'm talking about Gaze-Contingent layered optical see-through displays with the confidence-driven view volume. My co-authors are Alexander Plopski, Dieter Schmalstieg, and Denis Kalkofen. And to quickly start, so in this work, we wanted to build an optical see-through HMD, and you can see this here on the top right of the slide. This is our lab prototype. With the goals in mind that it provides at least near correct focus cues. It solves the divergence accommodation conflict, and also it shows content with optimal contrast. So essentially, we can say that we wanted to basically improve the user experience when wearing these HMD. As for our contributions, so the first one is basically our main contributions, and I will mostly talk about this, is that we present the first HMD which dynamically adjusts the position and also the working volume based on eye tracking confidence. So I will explain this throughout the presentation, what this actually means. We also have some other contributions. We present the first automatic multi-layer calibration routine, which can be applied to any multi-layer display. And also we demonstrate the first approach to compensate the change in field of view in a varifocal display automatically. And finally, we present a novel focal stack decomposition approach in the paper as well. All right, so to quickly start, I want to give a quick overview of related displays that also try to solve divergence accommodation conflict. So first of all, we have varifocal displays. And varifocal displays, we basically measure the current vergence distance of the user, and then we shift the image plane towards the measured distance. It's great because that means content is now displayed where the user is verging or focusing to. But as you can imagine, this depends on the precision and accuracy of the eye tracker, how well this works. Then we have multifocal displays. So instead of having a single image plane that's shifted towards the measured distance, in multifocal displays we stack multiple layers and combine them additively, for example, through beam splitters. So you essentially divide your scene into several discrete layers. Here, the downside is that if you want to support a large accommodation range, your display ends up being quite bulky because you need at least 4 to 5 layers. Next up, we have light field displays. These displays emit a light field, either through a microlens array or through a stack of spatial light modulators, such as transparent LCDs. And since you recreate basically a light field of a scene, these displays, by definition, support at least near correct focal cues. And finally, we have holographic displays. And they have also been researched quite a lot in recent years, and their image quality has improved also quite a lot through machine learning approaches, but they're still not quite on par with the image quality of the other approaches. But the work that's maybe most related to our current work is the video see-through system we presented in 2022, where we combined a varifocal and a multi-focal display. So essentially what we do is, instead of shifting a single image plane, as in varifocal displays, we now shift a two-layer multifocal display towards the measured vergence distance of the user. And this essentially allowed us to mitigate a certain error in eye tracking, because within the two layers, users can focus freely within the multifocal volume. And this allowed us to basically display content with more contrast compared to the other display types. However, this system still had a static display volume size. And then the question, of course, arises, how do you choose the static volume size? Of course, you can look into the literature and reference some average eye tracking error. But once you've set the static volume, it's basically there and you can never change it. But anyone who's worked with eye tracking knows that eye trackers work differently for different users. For some users, it works really well. That means we need a small volume. For other users, it doesn't work that well, which means we need to increase the volume size. Also, inferring focus distance of the user depends on the scene. So for example, if I have a nice scene understanding with a pretty low, with scene with low depth complexity, I probably know where the user is focusing to, which would also mean that I need to reduce the volume size. So actually what we want is a dynamic display volume, and this is where our new display now comes in. Again, here on the right side, you can see the lab prototype. So instead of having a static display volume, we have now a dynamic display volume, and this allows us to present the content with optimal contrast. And with optimal, I mean here, we can adapt the volume based on the current eye tracker confidence. And also, instead of having like a multifocal display, we now use a light field display, which allows us to model occlusions pretty well as well. So how does this system work optically? You can see the optical path here. We have a backlight, and the light coming from the backlight is first modulated by a rear LCD. This LCD is transparent, and then passes a front LCD. And then it is reflected by a mirror, refracted by a lens, and then combined with light coming from the real world via a beam splitter. So it's a pretty simple optical system, actually. This is how it works mechanically. So in order to move the layers, we put some actuators in the housing here. Also, the layers are mounted on some guide rails, and we used some end stops to get absolute positions for the layers. Here you can also see how the two image layers can be moved independently. Okay, that's great, but what impact does this have? So this video shows a through-the-lens recording of our prototype, where we basically have a butterfly that's virtual content and a tablet. And you can see the current display volume on the left side in the blue area. And at one point in the video, the volume shrinks because it adjusts to the knowledge that the user focuses on the iPad, which means we have good knowledge of the focus distance. And then you can see how the contrast improves. So here the volume is quite large, and now the volume has shrunk, and you could hopefully see how the butterfly increased in contrast. And also we can, of course, move the volume towards other distances as well. Maybe I can play this quickly again. Or here you can see a side-by-side comparison of this. On the right side, you can see, hopefully, that especially the wings of the butterfly have higher contrast, and also the text, for example, than on the left side. And so to quantify this result, we carried out some simulations and measured the relative contrast, and compared it also to other display types. So here our system is the blue line, And the varifocal system is the red line, and conventional displays the light blue line, and light field stereoscope is the green line. So especially in this simulation, conventional light fields and the light field stereoscope and the conventional display, they perform pretty poorly. But what's most interesting here is that the varifocal system, for a small focus distance uncertainty, still outperforms our system. But this is to be expected. If you are really certain where the user is focusing to, a single layer is just enough to basically show content with good contrast. However, since our system has individually controllable layers, we also have the opportunity to simply use our system in varifocal mode. Use our display as a varifocal system. It's a single layer varifocal system. And that means when we measure the focus distance uncertainty of the eye tracker, we can simply use it in varifocal mode once it's smaller than a certain value. And actually now our system is marked by these dots here, which means we always try to provide the optimal contrast. So some through the lens results. So this is shot through our lab prototype, where we also compare it to certain display types. And for our system, we have actually two images, ours best and ours worst. Ours best means basically the actual focus distance uncertainty corresponds to what we measured. So this is the best case, essentially. And ours worst means that we slightly overestimated the eye tracking confidence, and the actual focus distance of the user is outside now of the display volume. But as you can see in these insets here, it still shows content with relatively good contrast compared to the other display types, even in the ours worst case. Okay, to also quickly talk about the other contributions. First of all, the multi-layer alignment. Here we present basically a contribution where we can automatically align the two layers of the display with a camera placed in front of the HMD. This is just a before and after comparison. And related to that, we have the magnification in field of view. So as the layers move, their distance to the lens changes, of course, and that makes the magnification of the display also, or the layer also change. And we need to compensate for this, otherwise we get some pulsing motion, and also the layers, or the pixels of the layers are not aligned anymore. And thus we demonstrate in the paper a automatic calibration approach for this effect. And on the left side you can see the effect without any compensation applied, and the right video shows the magnification compensation applied. So hopefully you can see how this pulses quite a bit, and after applying the software correction, the pulsing is more or less gone. You can also see how the chromatic aberration is affected by this. It's a bit corrected as well. All right, so essentially that's it. If you want to know more about the paper, please scan this QR code that leads you to the project page, where you can see additional results. Of course, also some tables with nice numbers, and simulator results as well. And with that, I say thank you, and open for questions.
Okay, thank you, Christoph. So questions from the audience? Oh, yeah. Hey, Arafin.
Hey, this is Arafin from Colorado State. So great presentation, so great display. I have some two confusions on that. Like first one is when you're saying that it solves the divergence accommodation conflict, it's any distance range is conflict is solved, or is for all, like is a near depth conflict is solving, or far depth, or is considering both?
So what I'm mostly focusing to is more like in arm's length reach, because this is where the divergence accommodation conflict is most pronounced, right?
Yes, like it depends on the display plan, right?
Yeah. And so so since you can move the display towards the distance where the user is focusing to, essentially now the focus of the eyes, the divergence of the eyes are aligned, and this is how we can solve it. I don't know if this answers your question.
Oh yeah, that's my second question is actually related to that divergence. So these things mechanically move back and forth to solve a vergence accommodation conflict, right? Now, your eye tracker is estimating the depth, whereas their eye is looking at. So it's estimating the depth center of the display, rather than just any other peripheral or parafoveal position of the display, right?
So we can actually have two approaches how we infer the vergence distance of the user. We can, first of all, just calculate. So if you have a binocular eye tracker, you can calculate the vergence distance just by doing triangulation, basically.
Yes.
And you can also take your depth map and then intersect the gaze with the depth map, which gives you an additional.
Exactly, exactly.
Yeah.
You consider the both approaches? Or?
Exactly. So I actually prepared some additional slides for that. So here you can see we first use the vergence distance, like really the depth, where you just vergence to, and then we create. So this gives us one set of possible depth candidates, right? We can define this range by just looking up what is the calibration data of the user when calibrating the eye tracker. And secondly, we can then also use the depth map and intersect the user's gaze with the depth map, which gives us a cone. And then we can combine both sets to basically get a resulting set in which the final view volume is defined.
Great, thank you, thanks.
Thank you.
Great. Maybe one more question. Oh, Bruce.
Quickly, what's the speed to do the maximum distance, and then what's the visual artifacts for while it's moving?
Yeah, good question, thank you. So currently the speed of the lab prototype is just within 1 second. So I can go from 1 second from 3 diopters to basically optical infinity, which is not really enough to be unnoticeable. That's why we're currently working on further prototypes and then also to carry out a user study to really ask the users, okay, what are you additionally perceiving? Are there some additional artifacts that you are that you're perceiving when wearing the display? So this is something we still want to figure out.
Okay, great. So maybe next future application is like a ping pong game, like you have to change the version accommodation quickly. Okay, let's thank Christoph again, and then let's move on to the next talk. So the next paper, conference paper by Yuichi. Now we switch to Windows. Let's see how smooth they can connect. Okay, great.
Okay. So thank you for your introduction. So I'm Yuichi from Cluster Metaverse Lab, Japan. So today I'd like to introduce a new optical see-through display approach and called FactoredSweeper. So which both subtract and add the color of the see-through view while maintaining a compact form factor. So this is a joint work with Takefumi also from our lab, and Yuta, maybe you all know his face from the University of Tokyo. Sorry, okay, it doesn't work. And so our work is a series of optical see-through head-mount display. And optical see-through HMDs overlays virtual images on reality with beam combiners. So however, since optical see-through display only additively overlay virtual images on reality, so the virtual images appear semi-transparent. So as a result, OST HMDs are less visible in bright environment like this. So there are several approaches to mitigate these problems, and most conventional one is occlusion-capable optical see-through display, which is a combination of grayscale occlusion mask and additive, so virtual image, additive display which displays virtual images. So generally, spatial light modulators, SLAMs, are used for this occlusion mask, and such as digital micro mirror device, DMD, which is selectively modulate the brightness of incident light very quickly at a pixel wise. So however, a typical occlusion-capable optical see-through HMDs suffer from very large form factor because it typically requires two SLMs. So one is for additive display, so displaying virtual images, and the other one is occlusion mask. So to address this issue, so some researchers tried to implement single SLM occlusion capable OSD-HMDs like this, and which are generally using time division control using DMDs. And so this DMD switches on binary state, on-off state, and so when the DMD is on, so the virtual light is coming to the eye. In off state, so the real light is coming into the eye, and this DMD mix both states to display the virtual image. So, however, this approach have a limitation in terms of compensating background color, especially like this area, and because general occlusion capable OSD-HMDs only support grayscale occlusion. So in contrast, light attention display, so initially proposed by Yuta, and subtract the incident light using a pixel-wise polarized color filter, and so which acts as a colored occlusion mask. And so this initial prototype used a liquid crystal liquid crystal display for SLMs, but so recently we proposed stained sweeper and a single SLM light attention display, and that based on the high speed synchronization of DMD and tunable color filter. And at previous IEEE 2024. So this system can expand the color gamut and the dynamic range while keeping a small single SLM form factor. But so currently, so this prototype does not consider about addition of the light, and also it didn't consider about the background compensation. Currently, so this prototype is verified by using white background. So to solve this problem, so we propose an improved version of stained sweeper called FactoredSweeper, so which achieves both color addition and subtraction, and while keeping a compact form factor, just add a single white LED, and also supports background compensation. So this is our, the left image is our actual hardware setup, and the right is a schematic optical design. So we synchronized DMDs and non-pixel tunable color filter and the white LED here. And I will take a closer look at the operation of these systems. So first, when the DMD is turned on, and this DMD is positioned perpendicularly and on the entire optical design. And in this case, whether the LED is on or off, so the incident light passes through the holding optics like this, and is color filtered before reaching the eye. So also, if both LED and DMD are off, like this, so the DMD is tilted at the angle of white LED, and the incoming see-through view is occluded, like this. So up to this point, this is the same as stained sweeper, but this is a new feature. This is a new feature. So when the LED is turned on and the DMD is off, only the virtual light reaches into the eye. Then this light is then color filtered and reached to the eye like this. So to summarize, when the LED is off, so the real light is occluded or color filtered, so depending on the state of DMD like this. And also, so when the LED is on, and if DMD is off, so only the virtual light is coming to the eye, and if DMD is on, this is a very tricky part. So the virtual images cannot reach the eye because it is reflected, not perpendicularly reflected, and only see-through light is coming to the eye. So, and since we set several color filters as a primary colors, so these 4 modes are defined for each color filter. And so now we formulated this entire complex system so as a mathematical formulation, mathematical expression. And for now, we denote the background spectrum as R. And so at that time, so the DMD switches 0 or R, which are and the intensity of light coming to the eye. And also, so if we denote the LED spectrum as L, so the DMD switches between the L and R like this. And so we also denote the duration of color filter, each color filter, and the spectrum of color filter like this. And also we denote the DMD images as the ratio of the DMD is on at each color filter like this. And so finally we multiply and sum all of component and optimize and both duration of color filter and DMD images as G and H. So to solve the problem, we first convert this formulation as a matrix and convert spectrum to XYZ, and further optimize in CI lab domain and optimize this formulation with gradient descent approach using PyTorch. But this is a very complicated procedure. So please see our paper for detail. So actually, these are actual color filters like this, and these are images which displayed on DMDs, and the time schedule of each color filter to reproduce the target image like this. And this is a demonstration in our system. So on the left images are target AR view, and the background which set as a white background, and the subtract and the images on the left show the captured images from the subtraction and addition mode. And so from this, you can see that both the darker and brighter images than the background are displayed. And also, this video shows the longer the exposure, and the more images are integrated, and finally, the color image is reproduced. So to evaluate our method, we first simulated the reproduced images between various background intensity and compared them with conventional additive OST HMDs and subtract-only rotation displays and single SLM occlusion display and ours. And the displays that only perform subtraction and addition cannot support the dynamic range of changes in background brightness. And furthermore, single SLM occlusion cannot reproduce the color, especially in bright environment. In contrast, our method maintains high image quality across all conditions, outperforming other methods. So also we demonstrate this wide dynamic range quantitatively, by using image matrices like this. And next, we evaluated how the background compensation works. So in the simulation, we use a multispectral image with a high-resolution red background like this, and try to compensate this background image to display these target images. And so we confirmed that our method can outperform in all image quality matrices from the single SLM OCSST. And so in demonstration, we estimated the multispectral image from the color images taken from the viewpoint and used as a multispectral image and try to compensate this background. So why this is not the absolute ground truth value of viewpoint images, but we confirm that some of the brightest area can compensate by our approach. So in our paper, we discussed the remaining challenges of our system, including hardware improvements and real-time optimization and adaptive dynamic range control. So let me conclude my presentation. We presented one SLM integration of light acquisition and subtraction, light subtraction and addition, and provided formulation of perceived images and optimization algorithms, and implemented a prop type which reproduced images with background compensation. So this is the end of my presentation, and I'm happy to hear any feedback and comments. Thank you for listening.
Okay, thank you, Yuichi. So, questions?
I have a bunch of questions, but it's Akumado no Takai. Sorry, it's a Japanese joke. But so the white LED spectrum. So I think in the optimization process, I think the white LED spectrum is not considered.
So this one?
Okay. So okay. So you consider that. Okay.
Yeah.
So this is my first question. So sorry. The second question is: so can you optimize the on-off duration time?
So currently we fixed this ratio, off ratio, because in future we try to optimize all of ratio.
Is it possible to make if you optimize the LED on-off durations, then do you think you can further improve the image quality?
I think so. This consideration is including a kind of adaptive intensity control. So I mentioned as a future work because it should consider incoming light intensity and try to optimize all of ratio, including on-off ratio in LEDs.
I see. Thank you. It's a very interesting system.
Okay, any other Bruce?
So if I read the numbers right, this has a frame rate of 5 frames per second at the moment?
And so currently we support 30 frames per second totally.
Okay, but I thought the whole thing took
Yeah,
200 milliseconds.
Yeah. So we set 33 milliseconds, which means almost 30 FPS, drawing all of this loop.
Okay, and I get part of the problem with this is the switching speed for the mirrors.
Yeah, exactly.
That's you can't drive them any faster.
So it depends on the specification of hardware, especially for DMD.
Okay, thank you.
Maybe one more quick question.
So maybe the follow-up of the Bruce question. Maybe so you showed us the 200 millisecond photograph. That's why he thought it's a 5 hertz system.
Yeah.
And I also think that. So where the noise come from? Is it
So it's just the setting of camera.
cameras noise? So if you see by your eyes.
Yeah. So no, and if because it's because of very short exposure time. So for example, 20 milliseconds and 5 milliseconds. But if we capture the more good, better camera, so maybe this noise will be removed.
All right, then let's thank again Yuichi for the great talk. So we move to the final. Okay, let's thank. So the final talk of this session, again, another journal paper by, Rina. Great.
I'm Rina Nagano from University of Tsukuba. It's a great honor to be here to present my research. Today, I'd like to talk about Haptofloater Visuo-Haptic Augmented Reality by embedding imperceptible color vibration signals for tactile display control in a mid-air image. This work was conducted by the researcher here. First, let me start with some background. Imagine a scene from a movie where an image appears to float in the air. This kind of display has long been desired as an ultimate superior display expression. This image in the air is called a mid-air image. Nowadays, mid-air images are commonly seen in non-contact touch panels. This display uses a special plate called a retrotransmissive plate. Inside this plate, mirrors are arranged in a neat array, and two orthogonal mirror surfaces reflect light to form a mid-air image. The light from the image passes through the retrotransmissive plate, and the light rays are regathered at the plane symmetric position to form the same image in mid-air. The diagram on the right shows the side view of the image on the left. As shown in this diagram, when designing interactions between a mid-air image and a human hand or device, infrared and depth sensors are used to detect the hand or device. Therefore, the display of the mid-air image and the sensing of the hand or device are realized with different technologies, resulting in misalignment and time delays that do not map perfectly to the image. Some related research has solved this problem by embedding information in the image to control haptic devices. However, this method has the disadvantage that it requires a high-speed projector because the signal is embedded by switching the brightness at high speed. On the other hand, a technique called imperceptible color vibration has been proposed. This technique focuses on color instead of luminance and embeds the signal in the image. This technique takes advantage of the human characteristic that when two color images of the same luminance are alternately displayed, switching at a frequency of 25 Hz or higher, the human cannot perceive the switching, but sensors can detect it. In this method, we control whether each of the three RGB channels vibrates. This technique embeds information in the image based on the presence or absence of this vibration. In this way, information is embedded in the image according to its position, thus reducing misalignment and time delay. Our research explores how we can use this technique to add tactile feedback like texture to mid-air images. We do this by embedding signals in the image, displaying it as a mid-air image, and controlling haptic devices based on the signals captured with a light sensor. First, let me explain how we embed these optical signals into the image. We create the color vibration image by using a method that researches for color pairs that compose the color vibration at high speed. This method uses a color space fixed to the luminance of a specified color. We generate multiple color pairs that are symmetrical to the specified color, and from these color pairs, we extract color pairs that satisfy the conditions of color vibration to create a color vibration image. Next, we display this image as a mid-air image. We implemented a mid-air image display using a retrotransmissive plate, an LCD, and a vision control film. The LCD and retrotransmissive plate are placed at 45 degrees to display the mid-air image at 45 degrees to the ground. Now, let's talk about how we use these embedded signals to control the haptic device. When a hand touches the mid-air image, a photodiode detects the light signal from the mid-air image. A light sensing circuit processes this signal and sends it to a microcomputer. The microcomputer then controls the haptic device, which vibrates according to the signal received. The vibration part includes an audio module and actuator. We store the vibration patterns as sound files and play them back based on the signals received. We conducted several experiments using this developed system. The first experiment is a delay measurement experiment. The delay in this system is defined as the time from when the haptic device touches the mid-air image until the signal is detected and the device begins to vibrate. We conducted this experiment under turn-on and turn-off conditions, where the vibration is turned on and turned off respectively. The results show that the system's total delay was 59.5 milliseconds under the turn-on condition and 46.5 milliseconds under the turn-off condition. Since the time to perceive the delay between visual and tactile sensations is generally said to be 100 milliseconds, and this is larger than the total delay of the system. So it became clear that this system is designed so that the time delay is imperceptible to humans. We also ran a user study to determine how many milliseconds humans perceive a delay between visual and tactile perception in mid-air images. The image presented in the experiment is shown in the figure on the right, where the gray area is with no vibration and the green area is with vibration. We also conducted the experiment under turn-on and turn-off conditions. As shown in the video on the left, the participants were asked to put the haptic device and slide it between the gray and green areas. They were then asked to answer yes or no to the question of whether they felt a delay from the moment their fingertip entered the green or gray area until they felt the change in the vibration. Regarding the measurement conditions, we used multiple time delays. And 14 participants with the attributes described took part. The results are as follows. If the threshold for perceiving a delay is the time that user has a 50% chance of perceiving a delay, in turn-on condition, the threshold was 110.6 milliseconds, and the turn-off condition, the threshold was 112.3 milliseconds. This is quite large compared to our system's total delay, so we can say that a proposed system doesn't allow the user to perceive a delay between visual and tactile presentations. Also, compared with previous studies, in previous studies, there were physical cues such as force feedback in the middle image or touching a real object in the right image. The threshold in this case is about 100 milliseconds, which is about 10 milliseconds greater in the mid-air image. This is because there are no physical cues in the mid-air image, so the delay is more tolerable than when there are physical cues. Next, we conducted a user study to investigate how the user's perception of the texture's reality changes depending on the presence or absence and appropriateness of tactile presentation. We tested 3 different tactile presentation. No tactile presentation, a single frequency vibration of 150 Hz, or a texture vibration obtained from the database of textures with 5 different textures. Participants wore the haptic device and were asked how realistic was the texture material. They answered on a 7-point Likert scale for not at all to very much. 12 participants with the attributes described took part. The results show that reality was significantly higher when texture vibration condition than the no tactile sensation condition or single frequency vibration condition. This means that presenting texture vibration is an effective way to present realistic visual haptics textures. That's all for my presentation. Thank you for listening.
Thank you for the talk, Rina. So questions from the audience. Shohei?
Thank you for the nice talk and the interesting idea. I'm just curious about the, how can I say, the noises, that potential noises that the device would receive. Like, as far as I know, the optical devices, depending on the angle probably from the positions, it would receive some double images or something, as far as I know. So that then, is there any, how can I say, interferences from some, unexpected reflections to the device when you detect the
So, you mean, could you say that again?
So as far as I understand, the optic device would present some double images or something due to the leaking lights or something, depending on the positions. So
Yes.
is there any sweet spot to detect the correct signals, or if you have some noises, how do you handle those noises, basically?
A noise in the mid-air image?
Mm-hmm.
You mean, so it's a problem of display, you mean?
Yeah, like the mirror device would project multiple images or double images. So which means that if you assume that you only receive one specific patterns, and it could be the case that it just receives it twice or 3 times.
So you mean when the user moves finger?
Mm-hmm.
I see. So yes, that's good question. Of course, the finger moves, which in the system we show the movies. Then the color change over time. So the accuracy of perception may be decreased. So is that so?
I understand that the user cannot really perceive some differences between these, tiny differences in the signals. But my question was that your system can, how I'm going to say, somehow mitigate those noises or double images that potentially can affect these, how I'm going to say, disentangle these signals or something in your system. So is there any, problem due to that kind of, how can I say, double images?
There's problem for a perceiving flicker. It's 30 hertz color vibration, so users can perceive the flicker. Is it the thing you're talking about?
Maybe I can just catch up with you afterwards.
Oh,
Yeah,
thank you.
Maybe one.
Oh, does somebody else? Okay. It's a similar question, but a simpler question. How close does the finger have to be to the image plane before it starts detecting?
That's also a good question. At the moment, we know the sensor detect the light, the vicinity of the image plane. So at the moment, we don't know the accurate spatial area that detect the light. So for further research, we need to do experiment to know the accurate spatial area of detection.
Because you would get a sensation before you were actually touching the image plane.
Yeah.
And I guess the other thing too is if you pointed it up to a fluorescent light, you would get. So if you just had a flickering light in the room, you would get some sort of light vibration.
Yes, but I think the The vibration, the flicker of the light is 50 hertz in Japan.
Yes.
So, but the vibration is 30 hertz. So we cut the 50 hertz vibration in
Oh,
the.
So you do filtering? Okay.
Yes.
Okay. Okay. I think that
Yes.
was part of the question. Okay.
Thank you.
All right. Then let's thank Rina for the talk again. And this concludes the session. Thank you again. And let's cheer for the all audiences participants for the attending this session again. Thank you very much. Yeah.